the design phase itself, Okay, so that is the point, okay, that we have to clearly note down. Okay, so in low power VLSI design, actually it is the art of power analysis and optimization. It's the art of power analysis and optimization. And before moving into that, we'll try to know the difference between the energy and the power. Okay, so the energy consumed per unit time is the power. Energy consumed per unit time is the power, or energy is nothing but the integration of power over time. Energy is nothing but the integration of power over time. And if we evaluate for a single operation, okay, so we have to consider the limits as the time taken for the single operation. And then if we integrate the power, okay, with respect to time, then the expression for the power will be C VDD Vs into F. Okay, so where C is nothing but the load capacitance, C is nothing but the load capacitance, and VDD is the supply voltage, and Vs is the voltage swing, and F is nothing but the frequency of operation. F is nothing but the frequency of operation. So even though here we are writing the VDD and Vs separately, okay, both will be the same in most of the cases. That is, the voltage swing will be up to the full supply voltage. So Vs can also be written as VDD. So we can write V is equal to C VDD square F. C VDD square F. And E is nothing but your N into C into VDD into Vs. The only thing or the only observation what we can make from these two expressions is that your energy is independent of clock frequency. Energy is independent of clock frequency. That is what we can observe from these two expressions. But power is dependent of frequency. Energy is independent of frequency. That is, the energy required for operation, okay, is independent of the clock frequency. But the power is dependent of frequency. So reducing the frequency will lower the power consumption. Reducing the frequency will lower the power consumption, but it will not change the energy required to perform a single operation. It will not change the energy required to perform a single operation. That is what we can understand from this relation. Okay, so basically now we understood what is the power and what is energy, okay, and which is dependent on frequency and which is independent of frequency. And then what will happen if the frequency is reduced? That is, if we reduce the frequency, power consumption will reduce, but at the same time, the energy required to perform a given operation will not change. Okay. So we have certain power and energy figures of merit. Okay. So that is, the power consumption will be normally expressed in watt, that is known to all of us, and that determines the battery life in hours. Okay, that determines the battery life in hours. And peak power, that determines the power ground wiring designs. Okay, so in our design, always we have to make the ground wirings based on the peak power, and also that peak power sets the packaging limits also. Okay, that sets the packaging limits also, and that will have an impact on the signal noise margin and reliability analysis. So when we are considering these issues, then peak power need to be one of the major criteria. Based on that, we have to make we have to address all these aspects of the design. Okay? So energy efficiency in joules. Okay, so energy is normally expressed in joules, and that gives us the rate at which the power is consumed over time. Okay, and also energy is nothing but power into delay. Okay, and the lower the energy number means, yes. Right. Okay. So lower energy number means less power to perform a computation at the same frequency. Okay, less power to perform the computation at the same frequency. That is what we can understand. Other than this, we have energy density and the specific weight. Energy density and the specific weight. So what is energy density? So energy density is nothing but the amount of energy stored per unit volume or mass. Okay, the amount of energy stored per unit volume or mass. Okay, so this energy density is approaching that of explosives or explosive chemicals in the today's battery technology, and that needs a lot of concern. Okay, and also the specific rate. If you see, there is a stored energy per unit weight again. okay, stored energy per unit weight. That is doubling every several years. That is doubling in every year. Okay, that is doubling in every year. So the further increase in the specific weight, okay, if it is keeping on increasing, that will definitely draw safety concerns now because the energy density is approaching that of explosive chemicals. That is what we have seen in the previous. So this energy density and specific weight, because of its increase, okay, so that is drawing several concerns, drawing several safety concerns, okay. So this things need to be, or in order to reduce that also, okay, our power aware designs are going to be helpful. Our power aware designs are going to be helpful, okay. So as far as the battery technology is concerned, earlier we were using nickel cadmium batteries, nickel metal batteries, lithium ion batteries. The current technology is lithium-ion battery, and what are all these? Because it is a number of the rechargeable battery, we know that. Okay, and as far as the operation is concerned, the lithium ions will move from the negative electrode to the positive electrode during discharge, and also that will be in the reverse. Okay, when it is charging, So this is a common battery technology which is used in the consumer electronics sector currently. Okay, so that is known as. And what are all the advantages of lithium-ion batteries? So lithium-ion batteries have high energy density. Okay, high energy density. So we know that energy density is nothing but the stored energy per unit volume. Okay, stored energy per unit volume. So the energy density is more in the case of the lithium-ion battery. Okay, lithium-ion battery, and it has low self-discharge. Okay, so the self-discharge, all the battery technology will have a effect of self-discharge, and that is very low when compared to the other batteries. So lithium-ion batteries will have lower self-discharge, and it does not require any priming. Okay, so some of the rechargeable cells need to be primed. Okay, when they receive their first charge. Okay, whenever they receive the first charge, they need to be primed. Okay, so that priming is not required for the lithium-ion batteries, and also it requires very low maintenance when compared to the other battery technologies. Okay, no maintenance. That is, it does not require any maintenance. Okay, in order to ensure the performance. That is another advantage. And the last one, or the major one, is the no memory effect. Okay, so the memory effect is also known as the battery effect. It is also known as the battery effect or the lazy battery effect, which is nothing but that causes the battery to hold less charge. Okay? There is an effect which will have, the memory effect is an effect that causes the battery to hold very less charge. Okay? And always this battery technology, which has the memory effect, will remember the smaller capacity. Always it will remember the smaller capacity. Okay, so that memory effect is not in the case of the lithium-ion batteries. Lithium-ion batteries. Okay, so that is another advantage of the lithium-ion batteries. Various advantages of the lithium-ion batteries. Advantages of the lithium-ion battery. So, what is this low-power VLSI design all about? Okay, so there are two major aspects as far as the low-power VLSI design is concerned. Okay, it is nothing but the art of power analysis and optimization. Okay, so that is, what is analysis? Analysis is nothing but accurate estimation of power. Okay, accurate estimation of power. And optimization is nothing but bringing out the best code or best code without violating the, or best solution. Okay, bringing out the best solution without violating the specifications. Without violating the specifications. Okay, so power analysis is nothing but accurate estimation of power, and optimization is nothing but bringing out the best solution among the several solutions which are available without violating the specifications. Without violating the specifications. Okay, so these are the two major aspects of low power VLSI design. So always the analysis should precede the optimization, and if you are able to do the analysis properly, then the optimization can be done. Okay, then the optimization can be done in a proper way or a better way. Okay, so these are the two major aspects of low power VLSI design. Okay, so this is the note to us, that is the interest in low power chips and systems are mainly due to business needs as well as technical needs. So business needs, there are growing class of personal computing devices as well as wireless communications and imaging systems. And these systems demand high-speed computations, complex functionalities, and they often real-time processing capabilities also. Okay, and with lower power consumption we wanted. Okay, so because of that, there is always a need for low power VLSI chips. Okay, low power VLSI chips. On the other hand, if we see the technical needs, excessive power consumption is becoming limiting factor in integrating more transistors on a single chip or on a multi-chip module. So unless the power consumption is reduced, there is nothing need to limit the feasible packing and performance of VLSI circuits and systems. Okay, so that that is another need, okay, which arises from the technical side in order to move to the low power VLSI chips. Low power VLSI chips. Okay, so the need for low power VLSI chips, the need for low power VLSI chips, we have the following needs. Yes, we have the evolution process of integrated circuits, then increased market demand, then high performance computing systems, then environmental concerns, etc. Okay, so what is this evolution process of integrated circuits? So we know that we have already studied the Moore's law. So what are the predictions of Moore's law? So we have several predictions or several interpretations of Moore's law. Okay, so the Moore's law predicts the growth rate of okay, of your integrated circuits. Okay, the growth rate of integrated circuits. Yes, multiples of 2 for every 18 months. Okay, multiples of 2 for every 18 months. Every 18 months. Okay, on the and we have several predictions, but whatever may be the predictions. Okay, so the growth rate is rapid. The growth rate is rapid. Okay, so that is what we can conclude based on the several predictions of the Muslim. Okay, so the growth rate is rapid, and new generation of processing technologies are being developed every time. Okay? New technologies are developing every time, and the present generation techniques are at a very safe distance from the newer technologies also. Okay, so the fundamental physical limits, okay, that is having lot of limitations, and also a need for low power VLSI chips arise from the evolution forces of ICs. Okay, so that is the first reason why there is a need for low power VLSI chips. Then increased market demand, always we wanted the smaller and the lighter and more durable electronic products. Okay, so that is a reason why there is always a demand from the market as far as the low power VLSI chips are concerned. And as far as the high performance computing systems are concerned, and these computing systems are normally characterized by large power dissipation, okay, and that will drive a lot of consumes more power. The high performance computing systems consume more power, and the power dissipation of high performance microprocessors, if you consider, okay, so they are approaching several dozen watts nowadays. Okay, and that is also one of the reasons why we move on to the low power designs. Then finally, the environmental concerns. Okay, the environmental concerns. So the modern office equipment, what we are using, consume very large power, and that should account for a larger percentage of commercial energy usage. Okay? So improper usage of the power will definitely lead to environmental concerns. Okay? So that will have an indirect impact on the environmental concerns. Okay, so these are all the various reasons why we move on to low power designs. And why power matters? If the power is increased, power consumption is increased, that will increase the packaging cost. Okay, so that will complicate your power supply rail design, and the chip and system cooling costs are also will also increase, and noise immunity and system reliability with increased battery life will also get affected, and also it will have environmental concerns. Okay, so these are all the consequences of high power consumption. Okay, so that can be controlled by reducing the power. Okay, so where does the power goes in CMOS. Actually, as far as the CMOS circuits are concerned, we know that the CMOS inverter serves as the nucleus of all the design. Okay, so any design if we consider, okay, so that involves the CMOS inverters. So CMOS inverters are the nucleus of all the designs. Okay, so whatever analysis that we perform for a single CMOS inverter, that can be extended for any number of or any number of that is any complex designs. Okay, any complex designs. So that's why every time when we analyze the power, okay, we consider only a single CMOS inverter, So for a single CMOS inverter, you consider. So what are the potential sources of power consumption? If we see, actually there are four types of power consumption. First one is the dynamic power consumption. Then we have short circuit power consumption. Then leakage power consumption, and then we have static power consumption. Static power consumption, which is very common problem in pseudo NMOS logic. That's why in static CMOS we are not using, we are not bothered about the static power consumption. So that is not shown here. Okay. So if we see the dynamic power, okay, consumption will be 40 to 70%. Okay, today, and it is decreasing relatively because of the application of several power reduction techniques. And similarly, the short circuit power, okay, so that consumes around 10% of the total power, okay, and that also is decreasing absolutely. And the third source, that's the leakage power, that consumes around 20 to 50% of the total power, and today it is increasing because of the more number of devices which are getting integrated. Okay. And the static power, which I told, is not a common problem. Static CMOS design style, and it is a common problem in pseudo NMOS design. So we will not bother about the static power. Okay. So we will see each one of the source in detail. So what is the dynamic power dissipation? So we all know the configuration of a CMOS inverter, so which involves a PMOS transistor and an NMOS transistor, and whether it is an intentional, okay, or parasitic, always capacitance in the CMOS inverter. Intentional, we are purposefully designing for our design. Parasitic means that will get formed on its own. But whether it is intentional or parasitic, okay, so always there will be a load capacitance in the CMOS inverter, load capacitance in the CMOS inverter. And this load capacitance will charge and discharge during the operation. Charge and discharge during the operation. And this charging and discharging action of the capacitance will consume power. And that power is said to be the dynamic power dissipation. The power is said to be the dynamic power dissipation. Okay, so now in order to understand this, okay, so let us consider the resistive model of this CMOS inverter, the resistive model of CMOS inverter, and the CMOS transistor is modeled as the resistance RB, and the NMOS transistor is modeled as the resistance RN. Okay, and this charging and discharging action of the capacitance is modeled with the help of the switch. Okay, so when you have low to high transition output, that is at the input if we apply a high to low transition, then at the output of the inverter we will have a low to high transition. Low to high transition. So during the low to high transition, there will be a connection established from your VDD to the output. VDD to the output. Okay. So during that time, your capacitor will charge. This load capacitance will charge. On the other side, when the input is low to high, then the output will go from high to low. And when it goes from high to low, okay, the NMOS transistor contains and there will be a path existing between the NMOS transistor and the other ground and the output. Ground and the output. During this time, the capacitor will discharge. Capacitor will discharge. So this is the basic functioning of the CMOS inverter, and also the charging and discharging of the capacitor. And what happens? So according to the laws of physics, we know that the current okay, can be expressed as the load capacitance into the differentiation of your voltage with respect to time. So your I of t is equal to CL dV C of t divided by dt. So during the charging cycle, energy is drawn. Okay, so that is during charging cycle, the energy is drawn, and during the discharging cycle, okay, the drawn energy will be dissipated as heat energy. Okay, so how much energy is drawn from the source? That is expressed here. So that is ES is equal to integral V into IC of T into V. Okay. So we know that the energy is nothing but integration of power over time. So the power is expressed in terms of voltage and current here. So integration of V into I of T into dt. Okay, so we get here that is ES is equal to, we can substitute the expression what we have already seen for the current, that is I of T is equal to CL into dV of dVCL divided by dt there, and if we integrate the CL is constant, so that can be brought outside. Then we have integration of dVC of T divided by dt. We gets cancelled, and VC of dVC of T will become VC of T, and after the application of the voltage at the time instance at T1 and T0, okay, so at T0 there will be a zero voltage, and at T1 we will have a maximum voltage, that is a supply voltage, that is VDD. So that can be substituted here. So we get CL VDD square. Okay? VDD square. So during the charging cycle, the amount of energy that is drawn from the source is CL VDD square. CL VDD square. And the energy stored out of the drawn energy, how much energy is stored in the capacitor? How much energy is stored in the capacitor during the charging cycle? So that is what next we are trying to evaluate. So that is your capacitor. That is the amount of energy stored in the capacitor. That is cap is equal to again integration of T, VC of T, IC of T dt. That is the voltage across the capacitance and the current across your capacitance. Okay. So that will give us E cap is equal to half CL square, half CL VDD square. Again, after the substitution of your first expression, okay, that is the expression for your ICR. Okay, so that is the amount of energy stored in the capacitance. So if you compare this amount of energy with the amount of energy which is drawn from the source, this is exactly half of the energy. Exactly half of the energy. So that means out of the energy drawn from the source, half of the energy is stored in the capacitor. Half of the energy is stored in the capacitor. Okay, so next let us find out what is the energy dissipated at the RC, that is the charging, that is resistance RC. So that is EC is equal to the total energy drawn minus the amount of energy stored in the capacitor. So during the charging cycle, okay, 50% of the energy will be stored in the capacitor, and 50% of the energy will be dissipated as heat. Okay, that will be dissipated as heat. Okay, so what happens to the stored energy? Okay, so that we will see next time. So the energy dissipated at RD, okay, during the discharging. Okay, during the discharging, here you can see that as ED is equal to, since it's discharging, okay, we'll have a negative sign. So integral VC of T to IC of T dt, and that will give us CL VDD square by 2. So that means during the discharging process, again, the stored energy will be dissipated as heat. The remaining, that is the 50% of the energy which is stored in the capacitor, that will be dissipated as heat. Okay. So if the capacitance is charged and discharged, okay, F cycles per second, then the power dissipation of the system will be the energy drawn from the source into frequency. Okay, that will be energy drawn from the source into frequency, and that is given as CL VDD square into F. CL VDD square into F. Okay, so from this analysis, we can understand that. So out of the total amount of energy drawn from the source, 50% of the energy is saved in the capacitor or stored in the capacitor, and the remaining 50% is dissipated as heat during the charging cycle. And during the discharging cycle, the remaining 50% of the energy which is stored in the capacitor will also get dissipated as heat energy. So that means the energy drawn from the source, that is the electrical energy drawn from the source, will be converted into heat energy. Okay, fully. So that means this heat energy need to be properly dissipated, and also this power, it depends on what are all the factors that we can see from the expression. That is, the first parameters, the load capacitance CL, and then we have the supply voltage VDD, and then we have the frequency F, and also the switching activity factor or switching probability, that is T0 to 1, because 0 to 1 is considered to be an energy consuming event. Okay, so that is the probability for the energy consuming event 0 to 1. So that is also included here. So out of these three factors, that is CL, VDD square F, the dynamic power consumption is having a quadratic dependence with the supply voltage, because that is having a power of 2. Okay, quadratic dependence. The power, that is the dynamic power, is having a quadratic dependence with the supply voltage. So that means if we are able to reduce the supply voltage a little bit, that will have a major impact in the dynamic power reduction. Okay, that will have a major impact in the dynamic power reduction. Okay, so that is we can understand. And similarly, if we are able to reduce the load capacitance and the frequency of operation also, that will lead to reduction in the dynamic power. That will lead to the dynamic power reduction. Okay. So that is what we can understand. And also the switching activity of the circuit can also be reduced. If you are able to reduce the switching activity of the circuit, then that will also have a major impact on the power reduction. So out of the four factors, that is the load capacitance, supply voltage, then switching probability of the switching activity, and then the frequency of operation, the dynamic power quadratically depends on the supply voltage. So if you are able to reduce the supply voltage a little bit, that will have a major impact on the dynamic power reduction. Okay, so that is we can understand. So from lowering the dynamic power, we can reduce the minimum of these factors. That is the load capacitance, supply voltage. Okay, so activity factor or switching activity factor and the clock frequency. Are there any doubts or anything to be discussed up to this point? Am I audible to everyone?
Yes, audible.
Yes, sir. Thank you. Okay, so with this, we'll proceed to the next source of power consumption, that is the short circuit power consumption or power dissipation. Okay, what's short circuit? So the basic operation of the CMOS inverter is known to us. Okay, so when the input switches from low to high, then we know that there will be a connection established between the output and the ground, and because of that, the output goes from high to low. And how this connection is actually established? Because of the conduction of the NMOS transistor. On the other hand, when you have a transition from high to low in the input side, then at the output, you have a transition from low to high, and that will be because of the conduction of the PMOS transistor. Because of that, there will be a path existing between your supply and the output. So here, when you have a consecutive switching from low to high and high to low, during which there will be a moment for which both the transistors will be conducting. Okay, there will be a moment for which both the transistors will be conducting. And when both the transistors conduct for that moment, there will be a short circuit path existing between the power supply and the ground. And because of this short circuit path, there will be a short circuit current flowing from the supply to the ground. And this short circuit current consumes power. And that power is said to be the short circuit power. From low to high transition, there will be a conduction of your NMOS, because of which your output goes to high to low transition. On the other hand, when you have a high to low transition at the input, during which your NMOS will conduct, and the output goes from low to high because of the conduction of the NMOS. And when you have consecutive switching from 0 to 1 and 1 to 0 at the output, input, then there will be a moment for which both the transistors will be conducting. Both the transistors will be conducting. And because of the conduction of both the transistors, there will be a short circuit path existing between your power supply and the ground. Power supply and the ground. And due to which there will be a flow of current, which is said to be the short circuit current. And that current consumes power, and that is said to be the short circuit power consumption. It's short circuit power consumption. And this mainly depends on the slope of the input signal. Okay? So because the finite slope of the input signal causes a direct current path between VDD and ground for a short period. If the slope is high or it is gradually increasing, if it is not abruptly increasing, then in that case, what will happen? The existence of your short circuit will be for a longer duration, due to which the power consumption also will be more. Okay, so if we appropriately provide this signal slope for the transitions, then this short circuit path existence can be controlled. The finite slope of the input signal causes a direct current path between VDD and ground for a short period of time during switching when both the NMOS and the PMOS transistors are conducting. Okay. So, suppose the CMOS inverter voltage transfer characteristics. Okay, so you know exactly that is at this point. Okay, we'll have both transistors conducting. Okay, the moment at which both the transistors will conduct, and because of which the short circuit path exists. Okay, so. Okay, so this is again the analysis for your short circuit path. Okay, so that starts from the NMOS saturation current, and from that we can find out the I mean value, that is, and that comes to 4 by T integral tau 1 to tau 2. But tau 1 to tau 2 is nothing but the spins. That is the rise time of your input signal slope. Okay, is considered to be tau. And that next time, considering it. Tau. And within that, we are taking 3 different instances, that is tau 1, tau 2, and tau 3. Okay, so again, for the mean current, we can find out the short circuit current by taking the average short circuit current. Okay. So, and that can be evaluated, and finally, we can get the short circuit power as theta by 12 tau by T to VDD minus 2 VD the whole cube. So we know that theta is nothing but the effective transistor strength, and tau is the rise time of the signal slope, and then T is the time period for the entire signal duration, and then VDD is the supply voltage, and then VT is the threshold voltage. Okay, so the short circuit current depends on these parameters. It depends on these parameters. Okay, so the short circuit current depends on the duration of the slope of the input signal. Okay. There is again the impact of the load capacitance on the short circuit power is given here. So if the capacitive load is large, then the output fault time will significantly be larger than the input rise time. And if the load capacitance is small, then the output fault time substantially smaller than the input rise time. So that will be the condition. Okay. And here you can see the plot for the peak current as a function of the load capacitance, as a function of load capacitance. So when the load capacitance is higher, then you can see the peak current is less. And when the load capacitance is less, we have higher peak current. Okay. When the load capacitance is less, we have higher peak And also the short circuit power as a function of rise and fall times. There's a rise and fall times that is given. Okay. So again, it depends on the rise and fall time. So the rise and fall time should be appropriately fixed so that the short circuit power can be reduced. Okay, so the third source of power consumption is the leakage power. So what is leakage? Okay, so that normally exists as the natural phenomenon of the when the circuit is not in operation. Okay, when the circuit is not in operation, the leakage power consumption will be there, and this is normally not intended for normal operation. Okay, for normal operation, this is not intended, and also it serves no useful purpose. Okay, because except the power on the reset signal generation. For that application alone, it can be used. Otherwise, it finds no application or no usage. So this low leakage power should be power consumption should be avoided. Okay, so two major sources of CMOS leakage current are reverse biased PN junction and then subthreshold channel. Reverse biased PN junction and then subthreshold channel leakage current. So these are the two leakage currents which are commonly found in CMOS devices. So reverse biased PN junction, we can say that when source and drain, okay, we know the structure of the basic CMOS device. When source or drain of an N transistor okay, is at the VDD, okay, is at VDD, then what will happen? The PN junctions will get formed. Okay, the PN junction will get formed at the source of the drain of the transistors. Okay, okay, so the reverse biased PN junction leakage current is shown here. You can see we have the source, drain, and the gate. So when the source is at when the source or drain, okay, when the source or drain of the N transistor is at VDD, okay. On the other hand, if you consider the P transistor and if the source or drain are in the ground, in that case also the same thing happens. So when this happens, or when this condition occurs, then there will be a PN junction formation, okay, between the source or the drain of the transistor, source or the drain of the transistors, and because of the parasitic effect of the bulk CMOS device structure, the formation of PN junction will occur. Okay. So this PN junction current will be picked up through the bulk or the well contact, and magnitude of this current will be dependent on several parameters like the temperature and process parameters, okay, and what bias voltage we are applying, etc. Okay, so and also it depends on the area of the PN junction that is getting formed, the area of the PN junction that is also getting formed. Okay, so the reverse biased PN junction current, okay, it occurs as a natural phenomenon. Okay, and when the source or the drain is at VDD, then there will be a formation of PN junction. Excuse me. Thank you. So the junction current is normally this junction current will be picked up through the bulk or well contact, and it depends on several parameters like temperature, process, area of the junction, and also the bias voltage. Okay. So that is the reverse biased leakage. The subthreshold channel leakage. Okay, so that happens through channel. Okay, so the MOS device channel, and even though the transistors are logically turned down, and there will be a non-zero leakage current which flows through the channel. Okay, non-zero leakage current that will flow through the channel. Okay, but that will be very, very low order. Okay, it will be in a very, very low order. And this leakage current, we call it as some threshold because when it occurs when the gate voltage is below the threshold. Gate voltage is below the threshold voltage. Okay, so that the transistors are very less, I mean, very not active. They are not active. There is a non-zero leakage current through the channel and the microscopic level. And again, the magnitude of this leakage current also will depend on device dimensions and fabrication process. Okay, so the gate source voltage, drain source voltage, okay, and also again temperature. Okay. So these are the two leakage currents. So even though the leakage currents or the leakage power consumptions are very low, okay, due to the integration of more devices. So that is also coming into the main, one of the major contributors for the total power nowadays. So this is the plot for the leakage power consumption as a function of threshold voltage. Okay, for varying threshold voltage of 0.1 volt and then 0.4 volt. Okay, so how will be the variation that we can observe from this? And whenever we talk about the technology, we have several supporting technologies for low power. So here it is a 180 nanometer technology. Okay, so offered by DSMC processor. Okay, so which can be applied for low power designs. So we have CL018. G stands for general purpose or general. Okay, and then LP stands for low power, and the ULP stands for ultra low power, and HS stands for high speed. And the leakage power of these technologies are compared or highlighted here. Okay. So here you can see for ultra low power, the leakage is very less. There is 0.15 picoamperes per micrometer, 0.15 picoamperes per micrometer, and for low leakage, we can select the technology. Down we can select the ULP technology. We can select it, several technologies. So we support low power designs. Okay, so the exponential increase in leakage current. So that we can see that for 0.1 micrometer, 0.1 micrometer, 0.13 micrometer, 1.8 micrometer, and 0.25 micrometer, for which the leakage current blocks are shown. Okay, so for varying temperatures, when the temperature increases, you can see that in each technology, the leakage current also increases. So the leakage current mainly depends on the temperature. Okay, so and also it is higher in the higher technology, and in the lower technology, you can see that the low leakage current is low. The leakage current is low. So that is these are all the various sources of power dissipation. In the case of CMOS VLSI circuits, it's the dynamic power, short circuit power, leakage power, and one more power, there is the static power that is not shown here. Okay, that is not shown here. So these are some of the approaches for low power. That is, by reducing the chip and package capacitance, we can reduce the power. Then we can scale down the supply voltage, and also better power management techniques can be employed, and also better design techniques can also be employed for the reduction of the power. So as an attempt, in order to verify, okay, so what happens with the load capacitance, because we know that the dynamic power depends on the load capacitance. The dynamic power depends on the load capacitance. So as an attempt, we try to vary the load capacitance okay, for a CMOS inverter in these spikes. Okay, and we have verified the power consumption also. Okay, so this is the functionality. Okay. Here you can see when the CL is 1 picofarads, and it is varied to 10 picofarads and then 25 picofarads. Okay, when the capacitor increases, the power consumption of the CMOS inverter is also increased. Power consumption of the CMOS inverter also increased. Okay, and this was adapted in 1.25 micron technology. By varying the load capacitance, we can vary the power consumption. So for lower power consumption, we can reduce the load capacitance. So that we have tried. And similarly, when we moved from 1.25 micron technology to 0.18 micron technology also, okay, so the power consumption of the CMOS inverter got reduced. When technology scales down, we know that the supply voltage also scale down, and when we reduce the supply voltage, power consumption also reduces. And also, we have seen that the power consumption depends on the switching activity factor. Okay, so how switching activity of your circuit is more, then the power consumption also will be more. Okay. So as an attempt, we try to vary the switching activity of the input time. And for varying switching activity, we have evaluated the power, and we have found that when the switching activity is less, for which the power consumption is also less. The power consumption is also less. So power consumption also depends on the switching activity factor. Okay, it also depends on the switching activity factor. Say for example, if we consider a two-input NOR gate, if we consider a two-input NOR gate, so we have two inputs here. The output is out, and the truth table is given here. And from this truth table, we can find out so the switching activity factor for the NOR gate for a 0 to 1 transition. For a 0 to 1 transition. So, 0 to 1 transition switching activity factor is nothing but the probability of. Okay, so there is the probability of output being in logic 1. The probability of output being in logic 1 is 1 by 4. Okay. Out of 4 cases, your output is in logic 1 for 1 case. So the probability of output being in logic 1 is 1 by 4. And then you have the output being in logic 0, that is for 3 cases, that is 3 out of 4. 3 out of 4. So we can find out the switching probability for a 0 to 1 transition as 3 by 4 into 1 by 4. That is 3 by 16. 3 by 16. So this is the switching activity factor for the NOR gate. And if we proceed to the XOR gate, so we can see that the output lies in 1 for 2 cases out of 4, and output lies in 0 for 2 cases out of 4. So for finding out the switching probability or the switching activity factor, we can multiply these two probabilities. That is, we have 2 by 4 into 2 by 4, that is 1 by 2 into 1 by 2 is 1 by 4. So the switching activity factor for the 2-input XOR gate is 1 by 4. So which gate is having a higher switching activity? So 3 by 16 or 1 by 4? 1 by 4 is higher. Okay, so XOR gate has higher switching activity when switching activity factor when compared to the NOR gate. So in order to create the low power designs, we can employ the NOR gates instead of your XOR gates. Okay, so that is one thing what we can understand from this from these two slides. Okay. And also this switching activity factor is influenced by the signal statistics. Signal statistics. Okay, it is influenced by the signal statistics. So for each of the gates, so if you draw the plot, the three-dimensional plot, okay, so if you see the transition probability is strongly influenced by the input probabilities. Strongly influenced by the input probabilities. Okay, so the same thing we have analyzed for the NAND gate using MATLAB also. Okay, so this is the three-dimensional plot for your NAND gate. Okay, so that gives us the variation of your transition probability from a 0 to 1 transition. Okay, based on the input transition probabilities P and PB. So the distribution. And similarly for the NOR gate also, we have tried, and this was the pattern that has been applied for some time. And for XOR gate also, if we see, again we have we can see the influence of the input probabilities on the transition probability for XOR gate, and for NOT gate it's the case. Okay. And the switching activity factor or the transition probability for each of the gates are calculated, and it is found that for NAND and NOR have the same switching probability or the transition probability, and for the other gates like XNOR, XOR, and then NOR has higher switching activity factor when compared with the remaining gates. Excuse me. Anyone say something? Excuse me, I could not hear you. Ilangovan? Dr. Ilangovan?
Sir, hi, Mihir, sir. Yes, sir.
Right now, or I can continue for some more time?
Sir, your voice is low, sir.
Now it is clear, huh?
Yes, sir. Yes, sir.
Okay. Now we have to break, or shall I continue for some more time?
Sir, we can have the break and we'll continue again by 11, sir.
What time? What time?
11:13, sir.
Okay. So up to this, want to discuss, we'll discuss.
Audience, you have any queries regarding
Yeah.
so far the
Any
section?
queries, sir?
You can raise the question, or we'll go for break. Again, we'll continue from 11:30. So there is no more queries or a question. Yeah, you have questions?
No queries, so at what time we have to continue?
We'll start from 11:30, sir.
11:30.
Yes, sir.
Okay.
Yeah, thank you. We'll meet again 11:30. Dear participants, am I audible?
Yes, sir. You're audible.
This is regarding our attendance. No, the people, they have not yet put a single tick on their Google sheet. What it means that they never attended the meeting. So for the others, please check the Google sheet and make your attendance for today. Or you have any feedback or anything else you want to discuss, you can discuss. And one of the participants is asked the upload the materials document test in ATAL website. I think I hope that Friday I will do all these things. The test and all, we have only a single test, right? That test question will be posted on Friday.
Sir, again, the yesterday's spreadsheet in that we have to upload that.
Yeah, the people who couldn't make the edit in the spreadsheet, I'll make the edit. Okay, no problem. I'll put your attendance. You just make the message either in our group or either private chat. You make a message. What's your name and your college name? I'll put the attendance. Doesn't matter.
Okay, sir.
For others? Any other queries? No. Yeah, thank you. No doubts. Yeah, thank you. And one more thing, as per the schedule, schedule, today our afternoon session is cadence on section. Okay. Shall we go with that, or otherwise we'll have the hands-on session of HSpice today, and we'll have the hands-on session of cadence tomorrow. I'm expecting your feedback or your response.
Sir, hands-on exercise.
So shall we have the HSpice hands-on based on
Yes.
CNT FET? Shall we have
Yes.
that session today, and we'll have the cadence? Yes.
Yes, sir. Yes, sir.
Is it okay for all?
Yes.
For all attending, for these people? Is it okay for all?
Okay, sir. Okay.
Yeah.
Sir, we
This
want,
response yeah.
sir, two
Okay, sir.
input NAND gate using
CNT
two gates.
FET.
How to write the statements in SPICE we want.
For FinFET you are asking,
Two
right, ma'am?
fins. For two fins, sir. Two fins, how to write?
Two fins. It is very simple. You can change the pin number. That's it.
But
If you are asking
how
for
to?
two gate, I mean isolated gate, I'll show.
No, sir. NAND for NAND we require two gates. So how to write the attachment joining means how to?
That's what you are asking. You are getting your two gates means in FinFET isolated gates you are asking, right?
Yes.
I
Yes.
see. Not short gate. Short gate means we'll use both the gate will short and use as a
Shorted.
single gate.
Okay, not that.
Not that.
Not that. You should give
Okay.
individual input to A and B. A and B we have to give input. No, sir, for a NAND gate.
Okay.
So two I require for one PMOS, two gates. Generally in CMOS, we give two
Is this a
NAND.
question about MOSFET or FinFET, ma'am?
FinFET only I want. FinFET.
Yeah. Okay, fine. But actually, we have the schedule on CNT FET. Today, I have the plan of CNT based simulation. Anyhow, I'll tell during the code how to change the code in FinFET. I'll tell.
Okay, sir. Thank you, sir.
Is it okay, ma'am? Yes.
Okay, sir.
Sure.
Thank you.
Yes.
Thank
Sure.
you.
Sure. Yeah. Thank you. Yeah. Thank you. We'll go for break. We'll meet again by 11:30.